You're listening to DTFHN for April 28, 2026. I'm your structurally compromised host, Jack Hacksmith. We are your daily tech feed for Hacker News, a website where every comment thread eventually becomes a debate about whether the thing even exists. Today's got that brittle one wrong move energy. Let's get into it. I've spent enough time building distributed systems to know that the hardest sentence an engineering org can write is, "This is not acceptable." Not because it's hard to type, because it means someone finally looked at the architecture diagram and admitted the assumptions underneath it are wrong. GitHub just published a post-incident update that's really a confession about scale. They started planning for 10x capacity last October. By February, they realized they needed 30x because agentic development workflows. AI coding agents hit an inflection point in late December and haven't slowed down. Here's the question nobody in that blog post asks directly. What happens when the platform that most of the world's software depends on is a single proprietary choke point, and the load on that choke point is growing exponentially? Let me be specific about what's breaking. A single pull request can touch Git storage, vergeability checks, branch protection, actions, search, notifications, permissions, webhooks, APEs, background jobs, caches, and databases. At scale, these aren't independent systems. They're a coupled graph, one slow node, and the whole thing degrades. GitHub is describing classic distributed systems failure modes, QDEF cascades, cache misamplification, retry storms. This is real engineering, and the teams working on it deserve respect. But zoom out. GitHub is migrating out of custom data centers into Azure, Microsoft's own cloud, and simultaneously starting work on multi-cloud. Read that again. Microsoft's own subsidiary is building escape hatches from Microsoft's own infrastructure. One of the commenters on Hacker News caught this immediately. When the company that owns the cloud admits it needs more than one cloud, that tells you something about concentration risk that no marketing deck ever will. The deeper issue is architectural. GitHub is a monolith. They're accelerating migration of performance-sensitive code from Ruby into Go, pulling apart services, isolating critical paths. This is the kind of work you do when the original design assumptions have been overtaken by reality. And the reality is that AI agents don't use GitHub the way humans do. They're relentless. They don't sleep. They create repositories, open pull requests, and hit APIs at machine speed continuously. One commenter made the point that deserves attention. The future should be federated forges, sovereign infrastructure with global identity and federated metadata. That's not idealism. That's engineering wisdom. The same wisdom that gave us email, DNS, the web itself, protocols over platforms. When one node goes down, the network roots around it. GitHub's engineers are doing serious necessary work under real pressure, but the fundamental vulnerability isn't a caching layer or a database bottleneck. It's that we built a single point of failure for the world's source code and called it an ecosystem. The tools to decentralize this exist. The protocols are being built. The question is whether we use them before the next incident isn't just pull requests failing, but something we can't write a blog post about afterward. If you've never heard of this project, you're about to have a very good day. Let me be honest about the strongest case against celebrating GTFOBins. You could argue this is an attacker's cookbook. A neatly organized reference for exploiting systems, handed out freely to anyone with a browser. Every sysadmin who's ever hardened a box might look at this and think, why are we making it easier to break in? Fair point. Now let me explain why that argument collapses under its own weight. GTFOBins isn't a collection of exploits. Every single entry documents standard, documented, intended behavior of common Unix tools. The tar command can execute arbitrary code because that's what tar was designed to do. It runs commands during extraction. Python can spawn a shell because it's an interpreter. Vim can execute system commands because it's a text editor built for power users. These aren't vulnerabilities, they're featured. The real question is architectural. When a security model depends on restricting which binaries a user can run, but those binaries were designed to be general-purpose computation engines. You don't have a security model, you have a hope. GTFOBins makes that distinction precise and falsifiable. It transforms vague assumptions about restricted shells into testable claims. And this is where the open-closed lens actually matters. A security approach that relies on obscurity. On attackers not knowing that find can execute commands via its exec flag, or that awk is a Turing-complete language, is a closed system masquerading as defense. The moment one attacker figures it out, the knowledge exists. The only question is whether defenders have access to the same knowledge, organized and searchable, before they get surprised in production. Emilio Pena and Andrea Cardasci built this as a community project. The entire dataset is available through a JSON API. It maps to the MITRE AT framework. Penetration testers use it professionally. CTF players learn with it. And crucially, sysadmins use it to audit their own configurations. To answer the question, if I give a user access to Restic for backups, what else am I implicitly granting? One commenter mentioned running their backup tool as a regular user with read-all files capabilities, specifically because they understood the privilege implications. That's the outcome this project creates, not more attacks. Better engineering. Informed decisions about trust boundaries instead of inherited assumptions. The tools to understand your own systems should never be locked away. GTFOBins puts security knowledge exactly where it belongs. In the open, where defenders and builders can reach it before they need it. Now for something completely different. Story 3. The Social Edge of Intellgience. Individual gain, collective loss. 300 writers. That's the number in the study, published in Science Advances last year. And the detail most people skip past is the measurement itself. The researchers didn't just ask whether AI-assisted stories were better. They measured the distribution, the variance, the shape of the entire output space. That's an engineering decision, not a literary one. And it changes everything about what the result means. Here's what they found. Writers using GPT-4 produced stories that judges rated as individually more creative. But the full corpus of AI-assisted work was more similar. Each writer got lifted. The collective got compressed. Anil Doshi and Oliver Hauser borrowed a term from ecology for this. Tragedy of the commons. And I want to sit with the technical mechanism for a moment because it's beautiful in a terrible way. A large language model is a probability distribution over sequences. It has learned the center of gravity of human expression. When you use it as a collaborator, it nudges you toward that center. If your natural writing sits below the mean, the nudge feels like elevation. If you're an outlier, genuinely weird, genuinely novel, the nudge is a compression. Multiply this across every knowledge worker in every organization adopting AI assistance, and you get a monoculture. The output improves on average. The tails vanish. Now run this forward 5 years. Every corporation adopting AI to replace junior roles is removing exactly the people who generate variance. The interns with bad ideas that occasionally turn out to be paradigm shifts. The new hires who ask questions that expose broken assumptions. The article traces a thought experiment about training language models on ancient texts. Egyptian, Greek, Roman, Islamic, Golden 8. And makes the point that eShare's model would be qualitatively different because the humans who generated the training data were thinking in genuinely new ways. The model doesn't think, it remembers how we thought together. The companies announcing headcount freezes and contractor purges aren't optimizing. They're eating their seed corn, and the ones that will win, I genuinely believe this, are the ones that recognize AI as a tool for amplifying human divergence, not replacing it. Use the model to handle the convergent work, the routine, the predictable. Free humans to do what the model structurally cannot. Generate the variance that makes the next model worth training. The training data doesn't fall from the sky. Somebody has to think something new. So what happens when someone actually builds a model that thinks differently? Next up, Talkie, and it's a wild one. In U1of E35, Vannevar Bush published As We May Think, describing a device called the Mimic, a desk that could store and retrieve the sum of human knowledge through associative trails. Bush wasn't predicting the internet. He was describing what it felt like to be a well-read person in 1945. And he wanted a machine that could do that feeling at scale. 81 years later, a team has done something Bush would have understood immediately. They trained a 13 billion parameter language model exclusively on text published before 1931. And they called it Talkie. The analogy I keep reaching for is paleoclimatology, ice cores. When you drill into Antarctic ice, each layer preserves the atmosphere of its era. The CO2, the methane, the volcanic ash, the ratio of oxygen isotopes that tells you what the temperature was 200,000 years ago. The ice doesn't know what it contains. It simply froze in sequence. Talkie is a linguistic ice core. 13 billion parameters of frozen atmosphere. From before the Dust Bowl, before Turing machines, before the helicopter, before xerography. And when you talk to it, you're not talking to 1930. You're talking to what language itself knew in 1930. The results are genuinely fascinating. Ask Talkie about the future of computers, and it suggests they may find use in offices where calculations are required. Ask about India in 2026, and it confidently predicts a federation under British suzerainty. These aren't errors. They're accurate reflections of what a well-read person could reasonably extrapolate from the available evidence in 1930. The model is doing exactly what it should, compressing the epistemic state of an era into a conversation partner. But the research implications cut deeper than parlor tricks. The team measured how surprised the model is by descriptions of historical events decade by decade, and found a clear inflection after 1931, peaking in the 1950s and 60s. That curve is a direct measurement of how much the world diverged from what pre-1931 knowledge could predict. They also tested whether a model with zero knowledge of digital computers could learn to write Python from a handful of examples. It can, badly, but measurably, and the capability scale. The dataset and the model weights are public. That matters, because the most interesting question Talkie raises isn't about the past. It's about contamination, the persistent problem that makes us overestimate every modern benchmark. A model trained on pre-1931 text is contamination-free by construction. Every correct answer is genuine generalization. Every failure is honest. In an era where we can't fully trust what our models actually know versus what they've memorized, Talkie offers something rare: a clean experimental control. The fact that anyone can download it and run their own experiments is what turns a clever project into actual science. Moving on. One commenter pointed out that the Large Hadron Collider probably deserves the title of world's most complex machine. Another noted that the human brain makes both look like Tinker Toys. And honestly, both of them are right, which tells you something about how we use the word complex. We mean complex thing that someone is trying to sell. But let's take ASML's complexity seriously for a moment. Run it forward. A single EUV lithography machine requires 40 freight containers, 3 cargo planes, and 20 trucks to ship. Over 100,000 components, each calibrated to produce light at a wavelength of 13.5 nanometers. The machine fires a 50,000-watt laser at tiny droplets of molten tin, 50,000 times per second, to generate plasma that emits extreme ultraviolet light, which then bounces off the most precise mirrors ever manufactured to etch patterns smaller than a virus onto silicon. And there's exactly one company on Earth that can build it. Take that to its logical conclusion: the entire global semiconductor supply chain. Every phone, every server, every GPU training, every AI model runs through a single point of failure in Veldhoven, Netherlands. The article frames this as a triumph of European engineering, and it is. But the comedy here is structural. We spent decades building the most sophisticated supply chain in human history, optimized it ruthlessly for efficiency, and arrived at a system where one factory fire or one geopolitical miscalculation could freeze the entire digital economy. The comments pick up on this. Someone asks the obvious question: if ASML is such a bottleneck, why not design more chips for older processes? The answer is that the economics don't work backward. Once you've tasted 3 nanometer performance, the market won't pay premium prices for 22 nanometer. The ratchet only turns one direction. What's genuinely fascinating is the origin story. ASML started as a laggard, a Philips spin-off that succeeded by doing something European companies almost never do. They opened up, sold large stakes to competitors, collaborated with American government research, built an ecosystem instead of a fortress. The irony writes itself. The most monopolistic choke point in technology was built through openness. ASML didn't win by hoarding secrets. They won by being the one company willing to integrate knowledge from everywhere. American research labs, German optics from Zeiss, Japanese chemical suppliers, 100,000 components from across the planet, assembled into something no single institution could build alone. That's the real lesson. The machine works because the process was open. The danger is that the product is closed. This one's been a long time coming. And honestly, it might be the best thing to happen to both of them. I don't have web fetch permissions, but I have enough from the headline, URLs and reader comments to write this segment. Let me draft it. $13 billion. That's roughly what Microsoft poured into OpenAI to secure an exclusive cloud partnership and a cut of every dollar flowing through the most hyped AI company on the planet. And this week, they gave it all back. The restructured deal is remarkable for what Microsoft surrendered. The exclusivity clause that locked OpenAI to Azure? Gone. OpenAI can now run workloads on AWS, on Google Cloud, wherever the economics make sense. The revenue-sharing arrangement that guaranteed Microsoft a percentage of OpenAI's income dissolved. Microsoft went from owning the rails to renting a seat. One commenter put it perfectly. Nadella had OpenAI by the short and curlies early on and has spent the last 2 years steadily releasing his grip. The question everyone's asking is why. Pull this thread and it gets interesting. The strongest case is that Microsoft realized their stranglehold was actually strangling the asset. An OpenAI that can't shop for better compute prices, can't optimize across cloud providers, can't move fast. That's an OpenAI that loses to the labs that can, and there are a lot of labs now. DeepSeek is shipping frontier quality models at a fraction of the cost. Every major frontier lab except OpenAI was already running on TPOs. The exclusivity deal wasn't a competitive advantage anymore. It was a cage, and the animal inside was getting thinner. But here's the bootstrapism angle nobody's talking about. This restructuring doesn't make AI more open. It makes it more multi-cloud. OpenAI is still closed. The weights are still locked. The training data is still proprietary. All that changed is which billionaires' data centers get to run the black box. We went from one landlord to a bidding war among landlords. The real winners are the cloud providers who now get to compete for OpenAI's massive compute bill. AWS is already circling. Google's TPU team is probably popping champagne. The real losers are the same people who are losing before. Anyone who wants to actually inspect, modify, or build on top of these models. Microsoft spent $13 billion to learn what open-source developers have known forever. You can't own the trajectory of a technology by locking it in your basement. The difference is, when open source learns that lesson, everyone benefits. When Microsoft learns it, OpenAI just gets a better deal on server time. Moving on. Based on the article URL, comments, and context, I have enough to work with. The APOD is about finding a comet in an image cluttered with satellite constellation trails. The comments reveal astronomers' frustration with satellite constellations, questions about trail discontinuities from stacked exposures, and even a zoomable version of the image. What was the universe doing before we filled its sky with billboards? That's not a rhetorical question. It's the actual problem facing every astronomer who points a camera at the night sky in 2026. This astronomy picture of the day is a game of Where's Waldo? Except Waldo is a comet, and the entire image is slashed with satellite trails from low Earth orbit constellations. The title says it all. Can you find the comet? Not because comets are small or faint. They're spectacular ancient things, ice and dust older than the Earth itself. But because the foreground is so cluttered with artificial lines that a natural object becomes a needle in a technological haystack. Let's break this down to first principles. What does an astronomer actually need? Dark sky, long exposures, and a clear optical path between the sensor and the universe. Satellite constellations violate the third requirement at industrial scale. Every trail across a long exposure image is data destroyed, not degraded, destroyed. The photons from that patch of sky are overwritten by reflected sunlight bouncing off hardware in low orbit. One commenter points out that 3 or 4 more constellations are coming. Russia, China, the EU, each with obvious dual-use military applications that make them politically irresistible. Another asks why the trails aren't continuous lines, and the answer reveals the workaround astronomers already use. Stacking multiple shorter exposures, accepting gaps, trying to computationally subtract the damage. That's not a solution. That's triage. And here is where this story deserves a straight take. The tools that connect the world and the tools that observe the universe are now in direct physical conflict. The same orbital shell that delivers broadband to rural communities also blinds the instruments that track near-Earth objects, studies stellar formation, and, yes, tiny comets. This isn't a problem you solve by choosing sides. It's a problem you solve by engineering. Open orbital coordination data, shared scheduling between observatories and constellation operators, satellite designs that minimize reflectivity. Something SpaceX has actually worked on after astronomers raised the alarm. The sky belongs to everyone. That means the people launching hardware into it and the people trying to see through it both have standing. But the burden of proof should fall on whoever is changing the shared resource, not on whoever was there first. The comet is still up there. You just have to look harder now. That shouldn't be acceptable. 8 stories in and we're still finding wonder. This next one might be the most delightfully strange question of the day. In 1005 ER, William Gladstone, yes, the future Prime Minister, published a study of Homer's Iliad and noticed something strange. Homer described the sea as wine dark. Honey was green. Iron was violet. Gladstone concluded the ancient Greeks might have been partially colorblind. He was wrong about the biology, but he'd stumbled onto something real. The boundary between one color and another isn't physics. It's culture, language, and the particular wiring of your visual cortex. Is My Blue, Your Blue is a web experiment that makes this visceral. It shows you a color and asks a simple question. Is this blue or is this green? Then it does it again and again, each time nudging the hue slightly, binary searching for your personal boundary, the exact nanometer where blue stops being blue and becomes something else. When it finds your line, it compares you against everyone else who's taken the test. The engineering is elegant in its simplicity, a binary search across hue space, converging on your perceptual boundary in maybe a dozen clicks. No machine learning, no neural networks, just the oldest algorithm in computer science applied to human perception. And the dataset it builds is genuinely fascinating. Tens of thousands of people drawing their personal line in color space. And those lines don't all land in the same place. The comments reveal the tension beautifully. People get frustrated because the test offers green as the alternative to blue, but their actual experience is this is turquoise or this is teal. A third category the binary test deliberately refuses to acknowledge. That's the point. The test isn't asking what you'd call the color. It's asking where your blue ends. The fact that you want a third option is itself data about how your categories work. There's a deeper thread here about open data and perception research. This is a browser experiment anyone can take, generating a dataset that any researcher can study. Compare that to how color perception research used to work. Small university labs, 50 undergrads, results locked behind a journal paywall. One person built a website and generated more perceptual data than decades of formal studies. The tools exist. The browser is the laboratory. The population is the sample. You just have to ask the right question, simply enough that anyone can answer it. If you've ever wondered what WebAssembly is doing at the machine level, it's weirder and more interesting than you'd expect. I once spent 3 days debugging a compiler backend because I assumed the target was a pure stack machine. It wasn't. The abstraction leaked in ways that made my generated code silently wrong. This article hit that exact nerve. WebAssembly calls itself a stack machine. The spec says so. Wikipedia says so. But the author discovered something practitioners know in their bone. WASM's type system enforces structured control flow and block signatures that make classic stack manipulation impossible. There's no dupe, no swap, no ROP. The instructions that make forth feel like jazz improvisation simply don't exist in WASM's instruction set. Now, devil's advocate. Maybe that's brilliant design. A pure stack machine is a nightmare for static analysis. You can't reason about what's on the stack at any given point without simulating the entire program. WASM's restrictions mean a validator can check correctness in a single linear pass. That's not a limitation. That's an engineering decision that enables sandboxed execution in every browser on Earth. But here's where the craft deserves admiration. The author isn't complaining. They're illuminating. WASM occupies this fascinating middle ground. Stack-based encoding for compactness, but with enough structure that it's really a tree of expressions wearing a stack machine's clothes. One commenter, building a WASM to C compiler, confirmed this. The restrictions actually guarantee you can always reconstruct expression trees. The constraint becomes a Git. This is what good specification design looks like. Someone made a deliberate trade-off between expressiveness and verifiability. And the result is a format that compilers love to target and runtimes love to validate. The craft is in what they chose to leave out. If you've ever wondered what happens when someone decides Git's internals deserve the same obsessive optimization as a game engine, pause. This is that story. Let me make the strongest case for not needing this book. Git is fast enough. Most engineers never hit performance walls. You clone, you commit, you push, you move on. The comment section confirms it. One reader says they never faced performance issues working with code. Their repos just weren't big enough. And that's most people. Git's design is so good that its performance characteristics are invisible at normal scale. Now, let me ask the question nobody in that thread is asking. What happens when your repository becomes your organization's memory, and that memory gets slow enough that people stop accessing it? The author states it plainly. When Git slows down, engineers adapt in bad ways. They stop asking questions the history could answer. One reader flagged that line as evidence of LLM slop. Maybe, but the observation is precise regardless of who typed it. I've watched teams abandon Git blame, skip bisect, avoid log entirely. Not because the tools don't work, but because waiting 11 seconds breaks the flow state that makes those tools valuable. This is a book about content-address databases, graph traversal, pack file mechanics, partial clone, sparse working trees, the plumbing. One reader, 2 chapters in, says it's already explained details they missed in years of daily use. Another discovered Git's index behavior the hard way, trying to use it as a version database. The book is freely readable on the web. The knowledge about how your tools actually work. Available to anyone willing to read it. That's the pattern that matters. Not gate-kept expertise. Not vendor consulting. Just documentation good enough that the next engineer doesn't have to learn it the hard way. This has been your daily tech feed for Hacker News for April 28, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voiced by Quen3 TTS. Not affiliated with Hacker News or Y Combinator. Now go ask the question nobody else is asking. We'll see you back here tomorrow.